Assalamu alaikum warahmatullah. Um, in this video, we'll discuss the gradients of a vector valued function. We call that the vector valued function is a vector in the end. So it takes a vector x from Rn and maps it to Rm. From Rn to Rm. So here we have the vector x, which is mapped to another vector f of x. N and m does not necessarily are equal. Okay, so how we do that? What we do is like this. We decompose the vector valued function into its elements f1 and f2 until n, right? And then we take the partial derivative with respect to each element of x. So the first step is that we take the vector valued function f of x, right, which has here now m elements, so this should be m, right? So, now each element in this vector is a multivariable function, and we apply the gradient to this multivariable function. So for each function here, we take the derivative with respect to all the values, right? To all the values. In this case, the gradient becomes a matrix. It's called usually the Jacobian, right? So this is how we get. Now, in a compact notation, the Jacobian or the gradient, but usually in literature, when you have a matrix, it's called the Jacobian. You have a vector, it's called the gradient. In general, okay. So we take the derivative of this vector valued function with respect to x1, then x2, then x3 until xn. Each one of those is another vector, right? So we take the derivative of f1 with respect to x1, then f2 with respect to x2, x1, and so on, right? So here the ij element of the Jacobian is the derivative of the ith component of x with respect to the jth component of x. Again, so the jij element of the Jacobian is a partial derivative of the ith component of f of x with respect to the jth component of x, right? Okay, now a simple and important example is the linear function. Let's say that we have a linear mapping. We map x to a times x, and a is simply a matrix. So what is the dimension of a? A belongs to what? Right, it should belong to n here, and this is m times n, right? Okay. So if we apply the decomposition above, this is the vector valued function. So f1 with respect to x vector and f2 with respect to x vector, all the way down to f of n, f sub n with respect to x vector. Right. So each element of this is actually the row multiplication of a times this component x sub j, right? So if you want to take the derivative of this with respect to xj, you get the coefficients, the constants. Now apply this rule to all of the elements of f, you get the matrix, the same matrix A. So simply, if f is a matrix, so here what you're saying is that if you want to take the derivative of a linear function, it's the same thing as the case in the one dimensional, right? So x goes away and you are left with the coefficient a, right? Okay, now let's take a more involved example. Now we have a mapping. Okay, we have a function h of t. H of t is a composition between f and g. Okay, now here f is a multi-variable function, right? Because it maps a vector to a scalar. G is a vector valued function because it maps a vector, a one-dimensional vector in our case, to a vector, right? Here's f of x. It's an exponential of x1 multiplied by x2 squared, and the g is simply it's a parameterization of x1 and x2. So x1 equals, so here if we can say x1 equals t cosine t, and x2 equals t sine t, right? So if we want the derivative of h with respect to t, we use the chain rule. Take the derivative of x with respect to x and then multiply it by the derivative of x with respect to t, right? But we should make note that this is a gradient. So this is a gradient and it's a row vector. It's a row vector. Okay. But this is a column vector, right? This is a column vector. Okay. So we use the same formula as before, right? When we use the parameterization, partial f with respect to partial x1 multiplied by partial x1 with respect to t. This is the first component we added to the partial f with respect to x2 multiplied by the partial x with respect to t. We get this nice summation. Now let's write it down. I think we need to put it explicitly. Again, this rule. No, let's take this, right? Okay. Now let's again put the function. Sorry, so this would, yeah. Let's write down the functions. So here we have f of x is exponential x1 x2 squared. X1 is t cosine t, x2 is t sine t. Okay, let's write them down. Okay, again, so we have firstly let's put down the multi-variable function f of x vector equals exponential x1 times x2, this is x2 squared, and x1 is t cosine t, and x2 is t sine t. Okay, now we have the function h of t is f composed by sorry, so we have yeah, by x vector of t, yeah, and x vector is what, x1 of t and x2 of t, right? So we want to take the derivative of h with respect to t. So we apply the chain rule but with the parameterized form, right? So before that, let's write down the, let's take this, right? Let's write it down. So this is partial f over partial x1 partial x1 over partial t plus partial f with respect to x2 multiplied by partial xt with respect to t, x2 with respect to t. Okay, and let's write this rule again here for reference. So we have partial f with respect to partial x1, then partial x1 with respect to t, plus partial f with respect to x2 times partial x2 with respect to, sorry, this should be a 2, with respect to t. Now let's take each component and compute it alone. So the first thing we have is partial f with respect to partial x1. So what's the, let's zoom out a little bit. Yeah, so we need to derive this, right, with respect to x1. So we are deriving an exponential, right? So it stays the same, but we need to take the derivative of the argument with respect to x1, which is x2 squared, right? Why? Because the derivative of x1 is 1 and x2 is regarded as a constant. So this is the first thing. Okay, sorry about that. Right. Let's take the derivative of x with respect to x2. It's the same thing, right? The exponential stays the same. Now we want to take the derivative of the argument with respect to x2, which is 2x2, and x1 is a constant. We have 2x1 x2, right? This is simple, very nice. Now we want the derivative of x1 with respect to t, okay, which is the derivative of t cosine t. It's a product, so it's cosine t plus t sine t, right? And this here, x2 with respect to t, it's the derivative with respect to t sine, which is what? Sine t minus t cosine t, right? Now what we do is that we plug those values here, and after some algebra we should get this expression here, right? So let me see, I think I missed a sign, right? I missed a sign here, sorry. Yeah, I think the sign here is wrong, so this is, sorry, this should be minus and should be plus. Okay.